Hi, everyone. My name is Nivedita Mahesh, and I'm a grad student at Arizona State University. I work with Dr. Judd Bowman, and today I'll be talking about my study with Farside, specifically about its polarization configuration. Now, what is Farside? Farside is a probe class mission funded by NASA to place a low frequency radio array on the far side of the moon, with two main science cases in mind. One, to study the magnetospheres and space environments of habitable planets. Two, the dark ages and cosmic dawn, which we can't do from the Earth. So what does the far side array layout look like? So this is, I'm showing you a graphic here. There is the center rover with the base rover, and from which there will be 4 rovers that'll come out of it, and it'll lay out tethers that has antennas embedded in it. And the picture that's in the inset shows you how we're going to lay out the antennas, that is the dipoles. So what's going to happen is the rover is going to go out, the tether is going to come. One antenna will be laid out, the rover will turn 90 degrees, and the other antenna will be laid out, right? So there will be like 2 dipoles orthogonal to each other. So we'll get 2 polarizations, which is great. Now this layout offers few advantages. Let's go over them. For in terms of deployment, it's ease of deployment, right? Because you don't need robots, you don't need humans. The antenna is already embedded in tether, and the rover will take care of it. The next, it's robust. It's fail-safe because we have 4 rovers, 4 arms. Worst case scenario, we lose communication with one of the rovers. We can still lay out the remaining 3 arms and still do science. And then since we have 4 rovers deploying our antennas and not just one, we have spread out the mass. We're not like heavy mass on one rover. And we don't need stasers. So the antennas we are using are dipoles, and they are 100-meter long dipoles. So if you did not embed them in the tether, you will need stasers, right? And stasers had additional complexity, additional weight to our rovers. And in terms of science, we offer these advantages. That is, we can get better calibrations because each antenna has 2 dipoles. I showed you the orthogonal dipoles, so you can get easier calibration. So once you have dual polarization, you can also get circular polarization data, which becomes very important for the exoplanet science case. And finally, since you have dual polarization data, the integration time also goes down. Here, I'm also showing you another graphic of how the antennas are going to be laid out. So the tether from the previous antenna comes in. The first dipole, let's call it the X dipole, gets laid out. The rover turns 90 degrees, lays out the other dipole, which is the Y dipole. Now the rover and the tether goes on to the next antenna. So this is how it's going to be. Now here's where my study comes in. What is the significance? I want to study the polarization leakage caused by the far side array layout. Why? Because polarization information is very important for Farside. One example is the exoplanet science case. So the signal we're looking for from exoplanets is caused by the electron cyclotron maser, which is generally circularly polarized. So this helps us in separating the host signal from the planet signal, right? If we have circular polarization data, we can separate the two. In general, when you have an array, the instrumental effects causes polarization leakage and intermixing of signals. That's common in most arrays. What happens in far side, since there's an offset, remember that I showed you the X dipole is offset from the Y dipole, they don't have the same center. So because of that, there'll be additional mixing and additional leakages. So which is why we need to model them, understand these effects so that we can maximize the performance of the far side array. Let's understand this a little more closely. So like I said, in most arrays, for example, any array you take, OVRO, LW, MWA, Hera, all of these on Earth, all the antennas that cross dipoles are usually face-centered, which is what I'm showing you in a diagram here. So antenna 1 has dipole X and dipole Y, both of them have the same center. Antenna 2 also has dipole X, dipole Y, both of them have the same center. So this is how it's usually laid out. And when there's a signal coming in from a source from the top right, it first hits both the dipoles of antenna 1 and then both the dipoles of antenna 2. And when we want to make an image so that we can coherently add the signals, we take into account this delay, right? What happens in Farside? Let's add that offset. So now X dipole, you see the center of X dipole is slightly offset from the center of the Y dipole for both antennas, right? Now in this case, when the signal comes from the source, from the top right, same location, it'll first hit the Y dipole of antenna 1, then X dipole, again the Y dipole, and then the X dipole. So now when you want to coherently add the images, you not only have to take care of this tau delay we had before, but these additional delays too. So that causes that. This is why, intuitively to understand, this is why comes that excess analysis I'm doing. Okay, so what are the effects of it, right? First, let's look at the PSF and the UV coverage of Farside. Now, PSF is basically the eye of the array. What does the array see? The point spread function. And UV coverage is the sensitivity of the array, right? How many points are we sampling? So what I'm doing is I'm simulating the array layout. I told you the spiral arm layout that I showed. I'm just zooming in to the center to show how the offsets are looking. Now, the top row of the UV coverage is if you don't have any offsets. At the bottom is where how the UV coverage looks if there's an offset. So as you can see, visibly, you can see that they look different. One thing to note, the UV coverage of the offset case is much densely sampled, which is great. We actually have more points in space, so we are sampling it better and we're getting more sensitivity. And the last column here, I'm showing you the PSF, like I said, the eye of the array. So again, the top row is when you don't have any offset case, and the bottom is when you have offsets. Again, this is slightly different, and all of this has to be studied carefully. Okay, so now let's go into, so I showed you PSF and UV coverage, how they changed, right? So let's go into what the polarization leakage looks like. So polarization, just to note, to measure polarization, we use the Stokes parameters, I, Q, U, and V. Okay, so I'm going to see what the IQUV looks like. The way we do this, the simulation involves, I've simulated the 100-meter dipoles. I've simulated 2 of them orthogonal to each other, placed on regolith, and got the beam. Now I take the beam of both the X and Y dipoles. I take the sky, which has the IQ, U, V components. I combine that information in this linear fashion to get us Stokes information, right? Let's look at some plots to understand that. So this is the normal case, no offset, okay? So these are the plots. Now, in each of these circles, just to give you all an orientation, in each of the circles, the center of the circle is zenith. The circumference of the circle is the horizon. So this is like hemisphere, right? And in each, the first row is the sky eye leaking, the sky eye going into the instrument I, the sky I going into the instruments Q, the sky I going into the instruments U, and the sky I going into instruments B. So, and so on, each row. This was I row, the second row is the Q row, the third row is the U row, and the final row is the V row. So for an ideal situation, what we want is only the diagonal terms. That is, the sky's I is captured by the instrument I. The sky's Q is captured by the instrument Q. So on for the U and the V. Only diagonal is what we want. The off-diagonal terms should ideally be 0, but they're never 0 because just the beam, what I've done so far in my simulation is I've taken dipoles, I put their beam orthogonal to each other. This is on regolith. Just the presence of the dipole beam can cause this leakage into these off-diagonal terms. So it's always something to care about. Now let's add that little twist that Farside is offering. Now I had them centered at the same phase center. Now I'm going to offset my both X and Y dipoles by 50 meters is what Farside has proposed. Adding that, let's see how the leakage looks like. I'm going to the next slide. Just watch the diagrams change. And I'm going to go back and forth once, twice. Yeah, and if you look carefully, the maximum change occurs in the row of Q and V. I and Q is almost the same, but adding this offset causes a further intermixing of components that affects our U and V quite a lot. V more so, and we are really considered like concerned about V because, like I told you, in exoplanet science, we want the V polarization information. We want the circular polarization information so that we can separate the host signal from the planet signal. And by adding the offset, as you can see, without the offset to the offset case, the V polarization, the last row gets really corrupted. And this is where, and this is why the study I'm carrying out is very important. Also to note, this observation, this leakage that I've shown you is for one frequency, 2 megahertz. Farside is planning to operate from 100 kilohertz to 40 megahertz. It's a really wide band operation. And in that case, this effects increases more. It changes quite rapidly. Frequency, higher the frequency, this affects go increase even further. And errors in offset. So right now the offset, Farside team has proposed that they'll keep the offset 50 meters in X and Y direction. But even if there's a 1% error, the Stokes leakage gets even further worse. So another layer of complexity that goes into the study. Okay, so far I've showed you how the Stokes leakage looks. What does this mean for the sky, right? If I have an actual sky with sources and images, how does it look? Let's do that next. For that, I've created a simple pipeline that I'm going to show you here. So I take the sky sources, the separate sources. Let's say we have 3 different sources. Each of those sources I convolve with our beam. Now I get a convolved beam, convolved sky. I Fourier transform them. Now we have it in the visibility plane. I get the UV coverage for each of the sources. Okay, so I get the UV coverage for each of the sources, UV coverage of the array for each of the sources. Now we have the UV coverage and we have the Fourier transform beam convolved sky. We're going to multiply the two. We're going to inverse Fourier transform the whole thing to get images. Now we have individual images for each sources. We add them to get the final image. I'm just showing you this is the general pipeline. Right? Now this process I do for the Farside with offset and without offsets, just to compare, just to know like if Farside was not offsetted, what it would look like, and if Farside has offset, which is the actual scenario, what do the images look like? Okay, so again, these individual circles, the center of the circle, to remind you, is the zenith. The circumference of the circle is our horizon. The first column is Farside, but no offset between the dipoles. Second column is Farside again, but with the actual offset. The last column is the differences between the two. The first row is I polarization data. The second row is Q polarization data. Third row, U polarization data. Final row, V polarization data. Now, the input sky that I gave for this was 3 A-team sources. This year is Cygnus A, this is Cassiopeia A, and this is Sagittarius A. Right? And all of them, intrinsically, when I defined the sky, I said all my sources are I, right? So ideal situation when we process our sky through a pipeline, we should just only get I. But the beam effects, like you saw, the instrumental effects causes the image to leak into Q, U, and V, right? Let's see how much now. So as you can see, this is I with no offset, and you can see that there is some leakage in Q, but it's definitely 6 order, like it's 5,000 lower, right? And then U is even more lower, V is even lower, which is great. So no offset. In the case of no offset, if you had to take a ratio of V to I, it's actually 10 power minus 4, which is good detection sensitivity. Now let's look at the offset case. In the offset case, the I is same, very similar. If you want to look at the difference, is 10 power minus 30. Great. The Q is also roughly same to the no offset case. Again, the difference minus 30. But you can start seeing considerable difference. we actually can see more difference. Now, if we look back or think back to the slide where I showed you how the Stokes leakage looks like, when you add offsets, you see the effects more in U and V, not so much in I and Q. See, we are still in the same page, makes sense. But one important thing to note in V there is leakage, and if you have to quantify that, V to I ratio for the offset case is 0.033. It's like 2 orders of magnitude greater without offset, and that's really bad for the science case we're going for, right? So, which is why this is so important to model this carefully so that we can correct them when we get our final images. So this again, I'm showing you for 2 megahertz. Again, I have some numbers with 0.6 megahertz. I simulated that. The leakage, V to I ratio leakage is even worse. Again, so I'm also making a note of the analysis on U polarization because like I told you, offset also affects U polarization. For the 2 megahertz, the difference is about 160, which is about 50% increase in the U flux leakage, because the U flux leakage is initially 300 Janskis, and we have increased to 160. So yeah. And 0.6 megahertz, the U flux leakage is a little lower. It's 0.05%, which is not bad. But yeah, this is what I have so far. Just to summarize, the Farside layout has a spatial offset between the orthogonal dipoles. We really need that because it's easier for the rovers, right? Now, what happens in turn, it affects the UV coverage, the sensitivity of the array. It affects the PSF, which is the eye of the array. It affects the Stokes leakage. We saw that. We have developed a formalization to study the beam and offset effects. I showed you how, like, if I add the offset, we can study how much the leakage is. We have also constructed a complete pipeline that I can process point sources through the beams and the UV coverage of the Farside, like I showed you with Cygnus, CAS, and Sagittarius A. The future work is to answer the most important question, that how much tolerance in the error of the dipole placement and orientation can Farside withstand without affecting the sensitivity, right? So it already has an offset which we can model and take care of, but instead of 50 meters offset, if you give me a 50.1 and if you give me 50.2 for another antenna pair, how will that go on to continue affect our sky? That's an important question I'm trying to answer. Thank you. I'd be happy to answer any questions. How long did I talk for?
You did good. Absolutely.
Thanks. Did you understand?
How you